So we're very happy for this week's Institute for Quantum Studies seminar to have Olga Movilla come and speak to us today. So Olga did her studies, she grew up in Spain and did her studies in Barcelona, and then came here working at University of California, Irvine, with Trifon, her advisor, who we're happy to welcome today as part of our seminar. And she's an expert on stochastic thermodynamics, mostly focusing on classical systems. And today we'll be talking about or hearing about her work on thermal anisotropy. So Olga, happy to welcome you.
Thank you for the introduction and also for inviting me to be here today. So I'm going to be talking about the work that I did during my PhD at UCI, which is joint work with my collaborators Rifu, Jordi Ventura, Amir Tabai, Jongxin Chen, and my PhD supervisor Trifon Jojo. So the title of my talk is Stochastic Thermodynamic Treatment of Thermal Anisotropy. Now, I know this might be a mouthful for most of us in this room, so let me start by sort of explaining the different concepts that build up this title. So we're going to start, let me see, there we go. We're going to start with maybe the most familiar concept, which is thermodynamics. So thermodynamics, as we all know, is a branch of physics that sort of very roughly studies energy exchange. It was born from the work by Sadi Carnot in 1824 and sort of developed around during that 19th century. So it was born as a very powerful framework and also an extremely practical one. And sort of some of the most powerful sort of statements are put together in the thermodynamic laws. So we have the first law of thermodynamics, we all know about it, energy is conserved. And the second law of thermodynamics, which is the fact that the entropy of an isolated system can never decrease. So we can see how these statements are sort of extremely powerful and also very insightful in terms of how our world works. However, they do have some limitations because classical thermodynamics really is limited to the study of certain types of systems. So classical thermodynamics can only really have a macroscopic description of systems. So it can only study systems with extremely large numbers of degrees of freedom. This is the canonical example, right? Our container with gas and a piston. So here we have 10 molecules, but of course this would be of the order of 10 to the power of 23 molecules, right? So extremely large numbers of particles. Moreover, classical thermodynamics can only study systems at equilibrium, so systems whose properties don't change with time, unless we sort of externally manipulate them. So typically we're going to be interested in this sort of external manipulation, performing a thermodynamic transition, like for example, the Carnot cycle. So we would push this piston down and up, compress and expand the gas while heating it, cooling it to be able to extract energy from this type of systems. However, these transitions have to be quasi-static because the system has to remain at equilibrium at all times. So this in particular means that if I move the piston slightly like epsilon up, then I have to wait until all the particles equilibrate and then do it again and then wait again. So this transition takes like arbitrarily long times. And in particular, it really doesn't allow us to quantify power of this type of engines. So as a way to sort of overcome these sort of drawbacks, this next concept of my title comes along, which is stochastic thermodynamics. So stochastic thermodynamics was born around 40 years ago, and it's born as a theory sort of that is able to quantify thermodynamics at the level of single particle trajectories. Now, this doesn't mean that we're going to get our container of gas and track all the 10 to the power 23 degrees of freedom, but we're just going to take some that are more meaningful to us and some that actually have sort of a time scale separation with the other ones, of course, drain the rest, and then only track our degrees of freedom that we're interested in. So this is the typical sort of system that we're going to be looking at, like a Brownian particle, this big blue particle, in, for example, a heat bath of water. And these red particles would be the water molecules. So in this way, we can actually describe systems that are arbitrarily far away from equilibrium. And what this means in particular, that we can have finite time transitions, that we can have transitions in which our system goes arbitrarily fast. There's no problem in that. So this is nice because we can overcome those problems that we had in the previous theory. And how can we do this? Well, we need a model, and the way we're going to model this is through stochastic differential equations. So essentially, we're going to use some noise to be able to describe this interaction between our big blue particle, our Brownian particle, and the heat bath, the degrees of freedom that have a different time scale, and that we're going to sort of postgrade.
And so how do you distinguish this from kinetic theory, or Einstein worked out the Brownian motion of a pollen molecule, right? Yeah.
So I mean, this is basically what it is. We are going to go deeply and sort of deeper and define certain quantities that weren't defined at that moment. But I mean, essentially, Einstein got this Brownian motion, right? In terms of kinetic theory, I feel like in kinetic theory, you really try to track all of the degrees of freedom. So that's not what we're trying to do. We're not that sort of ambitious. And this makes it more more easy to work with than kinetic theory. So, okay, so let me show you maybe the most intuitive model that we can have, which is the underdamped Langevin equation. So this looks like a little bit like a mess, but this is really nothing but Newton's equation. So here we have x, the position of our Brownian particle, and nu, its velocity. So we have simply the derivative of x with respect to times the velocity, and mass times the acceleration is simply the summation of forces. So here we have three different forces. So we're going to first consider a potential force U, a potential energy U, that we really will think of as our control. And this is typically the setting in experimental setups. So we're going to think of this T as time, but also sort of as our control parameter. And then we have other two terms, and these two terms really come from the interaction between our Brownian particle and our heat bath. So the first term is a frictional term, so it's just trying to capture the fact that these red particles are going to try to oppose the movement of the Brownian particle. So this is linear friction, and gamma is the friction coefficient. And then we have the second term, which is sort of a dual term, and this is where Einstein sort of came along, and is the realization that because we have friction, we also have to have some thermal excitation, which comes from the fact that these particles in the heat bath essentially are at some temperature, and they sort of vibrate, they jitter, and they bump into this Brownian particle and exert some noise force on it. So this noise, this white noise, is modeled by this B, this Brownian motion, and this term has to be proportional to the square root of 2 times gamma, which is the friction coefficient, Kb, the Boltzmann constant, and T, the temperature of the heat. So here we have sort of maybe the most, as I said, intuitive model, and it's a really nice model, and it really captures the physics, but it's also a kind of a hard model to work with because we have 2 degrees of freedom that are physically very distinct. So what is typically done is to take a sort of simplifying assumption. So what we're going to do is we're going to assume that inertial effects are negligible. This is the time scales that we're interested in are much, much larger than the time scales of the decay of the velocity, this m over gamma. This is essentially like taking formally the mass go to 0, so this is the massless limit. So formally, we can simply get rid of this term here and set m equal to 0 and get this frictional term to the left-hand side, use this relationship, the velocity is simply time derivative of the position, and we'll get to the overdamped Langevin equation. Now, the reason we're interested in this overdamped Langevin equation and the reason we're going to work with it throughout this talk, it's obviously because it's simpler, but also because it's really useful, because the sort of systems that we're going to study with through this stochastic thermodynamic framework are going to be mostly biological systems in which we really have sort of dense fluids in which we have our proteins that we're going to be studying, our DNAs, this molecular motors, for example. So this model has really been extremely useful and extremely powerful in stochastic thermodynamics because it can really be applied to these settings in which we have, first of all, low numbers of degrees of freedom, and second of all, large fluctuations. So fluctuations have a dominant role. So now we've defined our stochastic differential equation. This is the dynamics of,
Where does the square root of temperature scaling come?
So that comes from Einstein relations. So that essentially comes from the fact that you need your system to equilibrate to Boltzmann distribution when you have 2 degrees of freedom. And this is exactly the scaling that you need to have. And it's essentially describing that, and you see another system like in electric circuits, and we're going to see that, in which if you have friction, you really need to make, your physics work. You really need this sort of fluctuating term with a certain amplitude to make everything consistent. But yeah, that's a very interesting point.
It's a special case of the fluctuation dissipation relation.
Yes, totally.
Diffusion constant proportional to temperature.
Yes. So, okay, so we have this stochastic differential equation as our model. And what this means is that if we perform an experiment, we have a Brownian particle in container, then what we'll see is a trajectory, a random trajectory. If we perform it again, we'll see a different random trajectory. This is what it really means, right? But we can have an equivalent description instead of looking at these random trajectories individually, we can also look at sort of an ensemble of these Brownian particles. And this ensemble will be essentially characterized by the probability density function, this rho of t of x. So this rho of t of x is simply stating what is the probability of finding our particle at time t at position x. So this probability density function evolves because we have this type of differential equation, evolves according to this Fokker-Planck equation, which we have written here as a continuity equation. So here, to write this as a continuity equation, we have defined this v, this mean velocity, as minus 1 over gamma times these two forces, minus the potential force, plus some sort of entropy. So with this now, we have defined the dynamics of our models, define the dynamics of our model at the level of single particles and also at the level of the ensemble. And now to actually do some thermodynamics, we need to define how this particle exchanges energy with the environment and also with the external potential. So let's do that. So the total energy of a single particle will be simply given by its potential energy. And this again, because we're working in the setting in which inertial effects are negligible. So we can take the differential of this potential energy and we'll get two different terms. One term that accounts for how U varies with respect to T, which is our control parameter, and therefore sort of accounts for the energy that changes due to controlled degrees of freedom. And this is why we'll call this term the differential of work. On the other hand, this term sort of quantifies the rest of the energy that changes, which is the energy that changes through our stochastic degree of freedom. And it really quantifies the energy exchanged with the heat path. So we'll call it the differential of heat. Now, this really represents a first law at the level of single particle trajectories. So we have that if the energy of a single particle changes, it can only change either through work that is exchanged with the external potential or through heat that is exchanged with heat. So sort of nothing too fancy going on. Now, we can also look at these energies at the level of the whole ensemble. And in order to do this, the only thing we have to do is simply take sort of the expectation, take the average. So we can integrate our potential energy with respect to rho, and we will get the energy at the level of an ensemble. And we can do the same thing, and also integrate over time, integrate over a thermodynamic transition to get the work and the heat at the level of an ensemble over a thermodynamic transition from 0 to TF. So the thermodynamic transition will be essentially characterized by this rho changing as a function of time. So we can do the same thing for the whole first law and get to the first law at the level of an ensemble over a time interval. Again, this is simply stating that if the energy of our ensemble changes, it can only change either through work that is exchanged with the external potential or through heat that is exchanged with the heat bath. So now that we've seen sort of how the first law is kind of built into this framework of stochastic thermodynamics, let me try to derive the second law. So the second law simply states, again, that the entropy of an isolated system can never decrease. In our case, our isolated system is the combined system of particles and environment. So we really have to take both into account. The entropy rate of the system is simply the time derivative of the sort of Boltzmann entropy of the system of particles, minus kb times the integral of rho. On the other hand, the entropy rate of the environment is given by Stochastic equality. This minus the heat rate divided by the temperature. This is really because we're assuming that the environment is sort of at equilibrium at all times. So when we put these two together, we sort of take the time derivative, integrate by parts, use the Fokker-Planck equation, and also integrate over time, we will get to the total entropy production over a thermodynamic transition from 0 to TF. And this
is worth pointing out here that capital T is temperature of the environment and not the system.
Yeah, correct. Yes. So here we have this constant gamma, the friction coefficient of the environment T, the temperature of the environment, and this constant is always positive. And here we have an integral over time from 0 to TF of the expected value of the square norm of this mean velocity. This means that in particular, all the terms in this equation are positive. So we already have derived really our standard second law. Now, the thing is that in the setting of stochastic thermodynamics, we can really do better than this. And we can really work in finite time and have finite time corrections to this second law. So how can we do this? Well, if we're interested in going from some distribution rho 0 to some other distribution rho df, we can simply minimize entropy production over that finite time interval, and we would simply minimize this cost subject to our dynamics, our Fokker-Planck equation, and to an initial and final fixed distributions. So we're lucky because this problem is really the subject of a field of mathematics that has been studied for more than 2 centuries. And this is the field of optimal mass transport. So optimal mass transport, what really does is...
Wait, let me slow you down. You're going really fast. Let's go back a little bit, just for the sake of everyone here. Let's slow this down a little bit. V squared, you defined V on the previous slide, right? So if we go back, let's go back to V.
Yeah. Here.
Good. So if you look at V, it involves the gradient of U, but also it also involves the gradient of the log of rho. So the distribution function, which is a time-dependent function, goes into the velocity as well.
Yes.
Right? So it's a complicated thing.
Yeah, but we really have control over this potential energy.
So you can control the potential energy, right? And you know what the temperature is, and you know this also expression in terms of U. Okay, so let's go back to your formula now. This guy. All right. So basically what you're telling us is that if you put all that stuff into this equation, you can solve for rho total, and it only involves the integral of this V squared you define times rho integrated over X.
Yes.
Fine. So that's nice because that says, you said that's a positive thing. So automatically the second law is true. But now we can go deeper and say, I want to try to then, now you say you want to minimize the total entropy. Is that right?
Yes.
Over what? What are we minimizing over?
So we're trying to find the optimal trajectory. So we want to find the optimal rho as a function of time and the optimal velocity that achieves this rho that performs our thermodynamic transition, which for us means that we want to get from point A to point B, from rho 0 to rho Tf.
And so tell everyone else, why do we want to minimize the total entropy?
So, I mean, we're going to see for me a good motivation later on, but I mean, for the sake of what I'm trying to explain now, I just want to find a tight bound on entropy production. I want to show that if you're trying to get from point A to point B, there's some unavoidable cost that you're going to have to pay, and I want to quantify that.
Okay, so the costs then we're defining as entropy production.
Yes, correct.
All right, are we all good now? Okay.
Okay, so as I was saying, this is precisely sort of what optimal mass transport looks at, and this is the optimal mass transport problem, which we call in the Benamou-Brenier formulation, so in this fluid dynamical formulation. And what this theory of optimal mass transport does essentially is it characterizes the solutions to this problem. So it turns out that the solutions to this problem can be characterized by the square of a distance in the space of probability distributions, in the space of which are essentially our thermodynamic states. And this is called the Wasserstein distance, which is squared between rho 0 and rho Tf. So what this tells us is that we really have a way in which we can sort of metrize this space of thermodynamic states, and the distance between 2 points will tell us what is the minimum entropy production that we have to incur if we are trying to move from rho 0 to rho Tf. Now, it not only does that, but it also allows us to measure lengths of any thermodynamic transition. So here we can go in very different ways from rho 0 to rho Tf, right? The optimal way, the length of the optimal path will be precisely this Wasserstein distance. So what this means is that this is a geodesic distance. But through this sort of Wasserstein metric, we can also measure lengths of other paths, and we can measure lengths of any given path. And this will be useful later. So, okay, so now we can use this solution to our problem to really bound entropy production by this thing here, which, you know, if Tf goes to infinity, then we recovered the standard second law, what we knew, you know, it simply has to be positive. But if Tf is finite, and if rho 0 and rho Tf are distinct, then this term will be strictly positive, and this will be the minimum cost that you have to pay in terms of entropy to be able to go from one state of our thermodynamic system to another. Okay, so another thing that will be useful for us later is that the optimal velocities that actually achieve this minimum entropy production have to be, in this case, have to be of gradient form. What this means is that in this setting, because as we pointed to, the only control we have is over the potential energy, we can really achieve these optimal velocities because we precisely have control over functions of this form. So this is all good news, and we can really essentially achieve this lower bound. Now we will see how this will no longer be the case when we have thermally anisotropic systems.
Just one thing, in the previous expression, it's interesting to notice that it's 1 over TF for the lower bound. So infinite time gives you quasi-static transition, so you don't produce any entropy.
And you see, but you see also inside the definition of this Wasserstein distance, there's a TF in front as well, right?
Yeah, so this essentially accounts for the scaling because optimal mass transport really studies to go from 0 to 1. But if you are parameterizing with constant velocity, which these are the optimal velocities, then this is essentially equivalent to putting this TF in front and integrating from 0 to TF. So this is essentially where it comes from.
Yeah, the TF is also there because there's also V square and DT, so the units to be right.
Mm-hmm.
Exactly.
It's not dependent on the rho TF.
Yeah.
So you're using this one as a definition of W2, or W2 has some sort of other definition, explicit definition?
I mean, for the sake of this talk, this is the definition. You can define it in sort of alternative ways, but I mean, they essentially boil down to this, to the solution to the optimal mass transport problem. Yeah, and this is really a distance, so it has all the properties of a distance.
And it also makes the space of densities almost a Riemannian space.
Yes.
You can define inner products very much consistent with this.
I didn't go into that much detail, but yes, we will see how, I mean, this underlies some of the things that we're going to talk about. So, okay, so now let me explain what do we mean by thermal anisotropy. So by thermal anisotropy, we mean that we're going to have different degrees of freedom in our thermodynamic system, each of which is going to be subjected to a different temperature. So here is a two-dimensional example. Here we have a 1 degree of freedom, x1, which is somehow coupled to x2 through some potential energy, and it's subjected to one temperature T1, while x2 is subjected to some other temperature T2. Now, the reason we are interested in this type of systems is because we can find, first of all, they have really interesting behavior, and we can also find this type of systems to describe really cool examples. So, for example, we have the very famous Feynman's ratchet. And this essentially is a heat engine that is able to lift some weight because of these two different heat paths, sort of tapping into these two different heat paths through two different wheels in a pole. But I mean, I don't want to go into the details of how this works, but I just want to point to the fact that we can think of this system as essentially having 2 degrees of freedom, each of the wheels, each of which is immersed in a different heat path, and they are somehow connected through some potential energy.
You're assuming the gamma is same for both of them?
Yeah, so throughout this talk, I will be assuming that it doesn't really matter all that much for what we're going to do today. You can sort of generalize it to different gammas. But
And you can think of x1 as like the angle of the ratchet,
yes,
for example, and
correct.
x2 would be some other degree.
So I mean, this is not the so what I'm really thinking of is typically you would have a sort of torsional spring in the middle, and this would connect them, and this is like what other people have studied. I mean, this
and then you'd have 2 degrees.
Yes, and this essentially gives us the exact same equations.
Okay.
So we're also inspired by other biological examples that said this is a theory that can be useful in the setting, and we really have a lot of proteins that live across our membranes, and this is an example of such a protein. This is the ATP synthase, and what this protein does is it essentially synthesizes ATP, which is sort of the unit of energy that our body uses. And it does so through sort of exploiting an ion concentration gradient. So we have this is a membrane, right, of our cell. So we have on one side of the membrane, we have a high concentration of hydrogen ions. And on the other side of the membrane, we have a low concentration of hydrogen ions. So this is an extremely complex system. Again, the scope of this talk is not to be able to describe this molecular motor, and I mean, it's not completely understood, but I just want to point to the fact that we can very broadly think of this system as a thermally anisotropic system, because we can think as having 2 different degrees of freedom, the 2 different subunits, which are somehow coupled with some energy. The upper subunit, it really is connected to this heat bath that has a lot of bombardment from these hydrogen ions, while the lower subunit has really less amount of fluctuations coming from this hydrogen. So as I said, this is a very broad description of the system, but I just want to sort of point to the fact that what we're going to try to do is sort of get the most basic characteristics of this type of systems and see what kind of sort of features we can uncover. So in particular, we're going to be focusing on a lot simpler systems, sort of minimal systems that have thermal anisotropy. And sort of the maybe most known system is known as the Brownian gyrator, and was introduced in 2007 by Riemannian. So what they came out with is essentially what we've seen, one overdamped particle that is able to move in 2 dimensions. So in one dimension, it will jitter a lot due to its hot temperature, and in the other dimension, it won't jitter that much due to its cold temperature. And it's kept in place by some quadratic potential, which in particular makes these dynamics linear, which makes them explicitly solvable. And this is one of the reasons, this sort of system captured attention. The other reason is that it displayed a very interesting behavior. So this behavior is actually also seen, I guess, essentially the same equations can also describe the physics going on in this electrical circuit. We can think of the 2 different degrees of freedom at the different charges at these 2 different capacitor plates. These charges also fluctuate due to these 2 different resistors being subjected to different temperatures. And this again generate this, because of this resistance and this sort of friction, again, we have this fluctuation dissipation relation, and we have fluctuation coming from these 2 resistances. So the reason why these 2 physical systems captured attention is because they display what we call non-equilibrium steady states. This is, if we leave this Brownian particle by itself and we just fix a potential, we can describe the system by its probability density, and its probability density will eventually reach steady state. It won't change in time anymore. However, the steady state will be very particular, because it will be such that there will be non-zero probability currents. This literally means that we'll have a particle on average sort of swirling around the origin. Now, the swirling motion doesn't really change the steady state probability distribution, but it does mediate heat transference between the 2 heat baths, therefore driving the system out of equilibrium. And these non-equilibrium steady states are really sort of a hallmark of life, because life by necessity operates far away from equilibrium, right? We cannot have this type of complex systems at this equilibrium state, at the state of maximum entropy and sort of maximum disorder. So we're going to really think of this thermal anisotropy as an example of a fuel that really enables life, that enables being out of equilibrium. And we're going to think of these different temperature heat baths as really valuable thermodynamic resources, as this like low entropy states that we can exploit to be able to extract energy from our systems, and also that we can exploit to be simply out of equilibrium. So one part of this talk, which is related to what Professor Jordan was bringing up, is that we are going to want to preserve these low entropy states as much as possible. And this is done by really minimizing entropy production. We really don't want to sort of lose this valuable resources. So with this as sort of an underlying motivation, also let me, before I move on to the actual work that we've done, let me just mention that actually these 2 different physical embodiments have been experimentally realized. First in 2013, this electrical embodiment, and then in 2017, this sort of colloidal particle embodiment, in which essentially you generate this extra fluctuations in one of the directions by some electric current that fluctuates. So I mean, it's really something that we can, make in the lab. So, okay, so with this as a motivation, let me now just go into the actual work that we've done during the last 4 years. I'm going to sort of focus on this first part, which is how to optimally harvest energy from this type of thermal anisotropy. And we're going to see how optimal mass transport geometry is going to play a predominant role in this problem. And then after that, I'm basically going to glance over some other projects. I'm not going to go into a lot of detail, but just so that you guys have a broader idea of what we've done. So let me start with harvesting energy. So we're going to consider, and actually, I guess throughout this talk, an n-dimensional system. So we have the same equation as we did before, but now X lives in Rn. And T is now a matrix, which is diagonal and has unequal entries. And this will allow work extraction. And this is essentially what I mean by thermal anisotropy, right? Each of the degrees of freedom, each of the X's is subjected to a different temperature. Now, the goal in this part of the talk is going to find the optimal control U that maximizes work extraction from this type of systems over a cycle. Now, over a cycle, we know from the first law, well, the energy doesn't change because we started in the same state. So the work output, which in this case is minus the work because of the sign convention we've chosen, is really nothing but the heat. So for us now, it's going to be more convenient to work with the heat. So that's what we're going to do. Now, it turns out that from our definition of heat, we can play around with it and essentially split it into two terms. This first term is linear and the velocity, while the second term is whatever. So this first term, we can really think of it, and here we haven't done it, as I said, we're sort of glancing over some things, but you can do this sort of formally, and this is really nothing but a line integral. This is some force and an inner product between a force and a velocity. So this integral really doesn't depend on how fast we go along the curve, on how we parameterize it, but only on the shape of this curve. This is why we'll call this term the quadratic heat. It really doesn't depend on how fast you go. On the other hand, we have this second term, which again is quadratic in the velocity, and you can maybe already remember that this is exactly the cost that we're minimizing in that optimal mass transport problem. So again, if TF goes to infinity, we can make this velocity such that this term vanishes. But if TF is finite, then this term will in general be non-zero. So that's why we call this the dissipative heat. So, okay, so now let us consider a cycle. And in particular, we're going to parameterize a cycle to this alpha, which we're going to assume that only has two dimensions. This is simplifying assumption. And this alpha is going to encircle a domain D. Now, this domain D is in the space of thermodynamic states, in the space of probability distributions. An example of how this can be sort of tangible, and an example we're going to go back to over and over again, is essentially the Brownian generator example, in which we have a quadratic potential and therefore linear dynamics, and therefore we can really have our system simply follow a Gaussian path. This Gaussian path is going to be with zero mean, and in this case, we're taking two dimensions. So the covariance matrix sigma is simply going to be a 2x2 symmetric matrix. So this 2x2 symmetric matrix has 3 degrees of freedom. We're going to perform another simplifying assumption, which is to assume that the entropy of our system of particles doesn't change in time. So the determinant is always constant. And in this way, we can now parameterize this Gaussian path only with two parameters. One is theta, that corresponds to the rotation of this covariance matrix, and the other one is r, and corresponds to sort of the relative magnitude of these two eigenvalues, of this metric. So in this way, we can really see how sort of this lambda1 and lambda2 can really take something like more tangible, which are going to simply be our parameters that essentially characterize our covariance matrix R and theta.
So let me stop you here again, just so we're all on the same page. So you have some kind of control parameter that you're dragging through this, you're dragging the particle through some kind of control space, and that's your alpha parameters, right?
Not quite. That's a catch. So now we're looking at parameterizing the space of distributions. So you're going to have a one-to-one relationship between alpha and your control parameters.
I see.
But alpha really.
So you're just characterizing the distribution of the x1 and the x2, and you say it's a Gaussian. You assume it's a Gaussian. So that's why you're talking about covariances and things like that.
Yes.
Because this is just parameterizing the space of distributions.
Yes.
We're constraining our models.
Yes, correct. So this is a particular case we're going to go back to several times, and this is the Brownian generator case, that case in which we can think of the capacitances, but essentially we have linear dynamics.
Got it.
But in general, we can think of a more general of, if you can parameterize your space of distribution in some other way, then.
So then the one are like the means of the Gaussian, is that right? Or not?
Sorry, what's that?
Are they the means of the Gaussian?
So here, okay, so here we're assuming that, maybe I should have done this more explicit, but we're simply looking at this picture in which we really don't have any control over the mean, but only over the covariance. And we're going to be essentially opening and closing.
I see. So you're
This
opening and
potential.
closing the potential.
Yeah, so we only assume we have, I mean, here we're just simplifying. We're trying to generate a sort of minimal engine. And we're only getting 2 degrees of freedom. Now, the way to do this with only 2 degrees of freedom, you have to sort of open and close and parameterize the covariance matrix in this way.
Okay.
So again, our parameters are r and theta sort of determines the rotation of this matrix. So if we have sort of an ellipse representing this covariance matrix, the theta is simply going to represent the rotation of this ellipse, while the r really represents the magnitude or the relative magnitude of the 2 principal axes of this ellipse.
Remind me, what is LC?
Sorry, I sort of was glancing over this, but LC is essentially, I mean, for us, it's just going to be sort of a property of our system, which is the characteristic length. And essentially, it's just going to carry the dimensions of length. So it's just to make this this r and this theta dimension less than much.
Is it related to the potential?
So yeah, totally. This will be related to the potential, and in particular, it will be related to the entropy that we fix for our system. So essentially, we're fixing the determinant of this matrix to be constant, and that's an assumption. And this LC is what is going to determine that entropy of the system, that the determinant of our matrix. So in particular, what if we're trying to understand this, what we can see is that if theta, this is a standard rotation matrix. So if theta is 0, then we really have a diagonal covariance matrix. And what in particular this means for this type of systems is that we have our 2 degrees of freedom, which are essentially uncoupled. What this means is that the system that is now uncoupled now really equilibrates to a normal equilibrium distribution. It's no longer non-equilibrium. So it's only when these 2 degrees of freedom are coupled that we really have this non-equilibrium steady states. So okay, but now let us sort of abstract a little bit back and look again at our quasi-static heat. So again, our quasi-static heat, because we have now this parameterization.
Can I say something? Intuitively, when they are coupled, there is some sort of a torque that is generated due to the circulation. And the advantage is steering this distribution in a circular manner. The shape of this takes advantage of the torque and translates it into work. And one of the papers, Olga's about impedance matching, etc., relates exactly how much the torque relates, but she's not going to talk about that.
A little bit.
All of this ties.
If we have time.
I don't know what.
Okay, so again, we're going back to our quasi-static heat, and we can write it now as this line integral over the perimeter that we're enclosing. Now, because we have this 2-dimensional parameterization, we can really write this line integral as an area integral using Stokes' theorem. So this area integral will be a weighted area, and this simply comes from using Stokes' theorem. Now here we have written it in a very sort of abstract way. We have an integral over the area, this domain D, times some function f, which is a function of our parameters, which really comes from Stokes' theorem. And this, we call it the work density. And this is essentially the differential of area. So we can think of this whole term as just D of A, which is in this special Riemannian metric. Now we can look at our particular example, at our Gaussian example, to sort of feel this a little bit more tangible. And for that example, this expression will simply be given by this other expression. So we can see how we have some function times the r, some function the theta, so simply a line, standard line integral. And then we can explicitly use Stokes' theorem to write it as an area integral. So integral over the domain of this d theta, dr. So here in this way, using Stokes' theorem, we can find our work density function, which is a function of r and theta. And we can plot this for this particular Gaussian case. And here we have plot. So here we have each of the points in this plane essentially represents a different probability distribution, right? It represents a different r and a different theta, which characterizes completely our Gaussian distributions. So what we see here is that if, for example, we go along this red curve, what we have found out is that the quasi-static heat is really nothing but the area integral over this enclosed surface, weighted by this work density that has been here color-coded. So the quasi-static work is really nothing but an area integral over a work density. Now let us look at dissipation. So dissipation again is characterized by this sort of square norm of this velocity. And as we've sort of talked about and hinted to, this dissipative heat can really be, for any given trajectory, can really be lower bounded by this constant divided by TF times the length squared of this trajectory and the length squared measured in this Wasserstein 2 metric. And the way to sort of achieve the optimal value is by parametrizing these curves optimally with constant velocity. So this length, again, in a sort of general way for our alpha, is simply the integral of the norm of the velocity of the curve, and this norm weighted by this Wasserstein metric GW. For a particular Gaussian case, this GW is simply a diagonal metric with, in this case, it turns out to be theta independent, so it's rotationally symmetric. And we'll see how this may be useful later. So again, if we go back to our plot, we have that if we're trying to go along this red curve, then minimum dissipation is really related to the square of the Wasserstein 2 length of this curve. So now let's put all these things that we've learned together to solve our problem. So again, we wanted to maximize work output over a thermodynamic transition. Now we can write work output as this constant times this difference between this weighted area and this length squared, weighted by some parameter mu. And this mu is nothing but the characteristic time of our system, so sort of a constant that is given to us, and TF divided by TF, which is the period of our cycle. So if we look at this expression now, this expression is independent on the parameterization of the curve because we've sort of gotten rid of that by assuming that we're going to parameterize it optimally with this length. So now the system, this problem is completely geometric. We just want to find the optimal curve that will maximize work output. So in particular, we can realize that this problem is related to an isoperimetric problem, which is that of maximizing a weighted area with having a fixed length. This isoperimetric problems have been studied for, supposedly millennia. And the sort of standard one is the one in Euclidean space. So it's the one in which we don't have weighted areas. And the lengths are simply measured in the standard sense, like Euclidean length. So we can think of this as grabbing our shoelace and trying to draw a closed curve. And then if we put it on top of the table, we'll soon sort of convince ourselves that the optimal solution for this, the closed curve that maximizes the area within it, will simply be a circle in this Euclidean case. Now, because in our case, we really have this sort of curved space, this Riemannian manifold of probability distributions, and we also have this weighted area, this problem is not going to be that simple, but it will still be sort of numerically tractable, of course, and we can sort of see this in this figure. So in this figure, what we have portrayed is here in this grid, this blue grid represents the work density function, and these lines represent the optimal curves for the problem, for this isoperimetric problem for different fixed lengths. So we can see how all of the curves try to go around this point of maximum work density, and how, as you know, the longer the curve, the sort of the broader the area that can be enclosed. Now, how can we use this to actually solve our problem of maximizing work output? We only want one curve, we don't want a family of them. So what we have to do is we simply have to find the optimal length that maximizes this difference between the optimal areas and this mu times length squared. So this can be clearly seen in this figure. So here we have plotted the solutions to our isoperimetric problem for different fixed lengths. So this blue line is the optimal areas for different fixed lengths. So if we plug this in there, the only thing we need to do is we maximize over the optimal length, and essentially we want to maximize this difference between the optimal areas and mu times the length squared. So essentially the maximum work output is simply given by the maximum vertical distance between this blue line and the line with constant slope mu. So it's simply given by this expression, by this distance. Now, because we've solved really this isoperimetric problem, we also have the solution to another problem 0.3, which is that of maximizing work output given a fixed efficiency. So I haven't defined efficiency yet, but I'm going to do so very shortly. But I just want to point, just believe me that this lines, sort of the points with constant efficiency will be located at a line. And then the maximum work output given a fixed efficiency, its operating point is simply at the intersection between the optimal isoperimetric line and the line with constant efficiency. And then the maximum work output is given by this vertical distance. So this geometric picture really helps us solve some problems we're interested in the setting of stochastic thermodynamics. Now, as I promised, let us look also at efficiency. So in this setting, we're going to define efficiency as this ratio between the work output and the quasi-static work. And this really makes sense because the quasi-static work is the maximum amount of work that we would be able to extract from any given curve if we were able to parameterize it in infinite time. So we were able to simply get rid of the dissipation. So of course, this work output is bounded by the quasi-static work. And so this efficiency is really upper bounded by 1. And this.
So maybe I can make a comment here. So usually a thermodynamic efficiency would be the work output divided by heat input from the hot bath. And so you've changed that definition here. Maybe you can motivate the change it.
Yeah. So the thing is that in this system, because we're in constant, we're connected constantly to 2 different heat baths, it's really hard to separate what is the heat that goes into the hot heat bath versus the heat that goes into the cold heat bath. And I mean, this was really a struggle for us when we were trying to define efficiency. And this is one definition of efficiency that you can have, but it's certainly not the only one. And this definition has good things. That is, it really takes into account this dissipation, but the bad things is that you really sort of put under the carpet the heat that directly flows from one heat path to the other. So that we're not accounting for in this definition of efficiency. And that was something that we were trying to work on, but it seems to be really hard to be able to put those things together to try to extract work output, but also quantifying or putting a stop into that lost heat.
The leakage from one to the other.
But yeah,
you calculated some of me.
Yeah, it's just like it didn't seem that natural. Then we're going to talk, maybe if we have time at the end of the talk, about entropy. And then we're going to see how this entropy really is able to capture this leakage. But energies in the setting are not that able to capture this leakage. So it's really whether you want to put this together it's really hard to, because I mean, essentially, to go from entropy to energy, you have to multiply by T. This T is now a matrix. So it's whether how you account for this T that makes the difference in the setting. But I mean, well, so right now we're going to consider this efficiency, and this efficiency, I mean, is useful because it again characterizes this dissipative losses. So what we're going to try to do is we're going to use our sort of geometric description of our system. In our geometric description, remember the work output is something like the area minus the length squared, and the quasi-static work is something like the length, the area. So if we put these together, we get to this expression of efficiency, which is 1 minus mu times this ratio between the length squared and this weighted area. Now, what we're going to try to do is, again, as sort of in a similar spirit that we had, we were minimizing entropy, we also want to bound efficiency so that we can account for this finite time, because this one bound didn't really account for the fact that we're working in finite time. So we want to account for that.
And can you remember what mu is? I forgot what mu is.
Yeah, so mu is this ratio between the characteristic time of our system and TF. So this is going to be extremely important right now. So, okay, so to bound this efficiency really for any cycle, what we have to bound is this ratio between the weighted areas and the length squared. And it's really nothing but to find an isoperimetric inequality in this sort of space of probability distributions. Because isoperimetric inequalities are precisely those that bound this ratio between an area and a length squared. Now, these isoperimetric inequalities are sort of families of isoperimetric inequalities, and some are sort of tighter than others, depending on the type of space you have. So what we're going to do now is we're going to go back to our Brownian gyrator example and exemplify how one can use those for their systems. So in our case, we had a rotationally symmetric metric, which means in particular that we can use this type of isoperimetric inequality. Again, this is a completely geometric statement. So it holds for any space with rotationally symmetric metrics. And it turns out that for our case, this inequality can be written in this way. So the length squared is lower bounded by 2 pi times the area. Now note that the area is an unweighted area, and we're really interested in weighted areas. So what we have to do is sort of go around it and lose some precision and multiply and divide by a weighted, this unweighted area, and then we can bound this ratio with our isoperimetric inequality, while we can bound this other ratio by simply the maximum f. So in this case, 1/2. And then we'll get to this bound on efficiency, that now it doesn't depend on the cycle you choose. It only depends on the geometry of your system, so on TC, and also on the cycle, on the period. So we can really have this finite time correction to this efficiency. And in particular, what this also tells us is that if TF is smaller than 4 pi times TC, this if we're going too fast, then this negative term will dominate over 1. What this means is that efficiency will always be negative, no matter how you choose your curve. So if you're going too fast, this can tell you that no matter what curve you choose for your system, you're going too fast. It's not going to be possible to extract any positive work. So this really brings me to the end of this first part, in which I hope we've seen how powerful, like a sort of a geometric picture, and how beautiful a geometric picture of and a geometric description of this kind of system can be, in which you really can write down statements for any curve. So now, if we have time, well, we have very little time, so maybe we can skip to one. I can just talk about minimizing entropy production. So these are some related projects that we have, but I mean, we don't have that much time. So let me just talk a little bit about the one that for me is most interesting and sort of more intrinsic to this thermally anisotropic systems, which is minimizing entropy production. And again, sort of the motivation for us is that we have those low entropy states, those different temperature heat baths that really allow us to do a lot of things. So we want to make good use of them. And a way to do so, if I need to go from point A to point B, is by minimizing entropy production. So in a very similar way as we did in the introduction, we can again define the entropy production in the exact same way and write it as this function. Now note that here we had before gamma over T. I mean, I don't know if you remember, but I'll just tell you, we had gamma over T. But now T is a matrix, so we really have to account for it somewhere else. It turns out that the correct way to account for it is by weighting this norm of the velocity by this matrix T inverse. So now the same problem as we had before here, I got rid of the details, but minimizing entropy production, we were able to show that again, can be quantified as this square of a length in the space of probability distributions, the Wasserstein 2 length, that is now weighted by this matrix T inverse. Now, what this theory of optimal mass transport tells us is that optimal velocities in this case are now going to be given by these expressions T times the gradient of a function. And here comes the problem, because we really only have control over this potential energy U typically. So then what this means is that through only this control, we cannot really achieve these velocities, because in general, this T is a matrix, it's diagonal, but we cannot really achieve these velocities. And this means that we really need non-conservative forces to follow this entropy minimizing trajectories. Now, as I sort of talked about, this is not typically the case in experimental setups. So in order to see how, if we are trying to minimize entropy production now by only using a potential force, then we really need to sort of essentially quantify a trade-off between the different things we can do. So let me, in order to show you this, and this is again in contrast with the other case in which T is the identity and velocities are simply the gradient of a function, and we really have control over the whole thing, and we can follow entropy minimizing trajectories. So let me decompose entropy production into two different terms. To decompose entropy production in this way, we have essentially decomposed the velocity field into the T times the gradient part and the divergence-free part. And this is essentially a generalized Helmholtz decomposition. But it turns out that you can split it into these two terms. So this chi is a divergence-free term in the velocity, and this T gradient phi is the gradient term. So if we had control over both conservative and non-conservative forcing, then what we can do is we can minimize this term using our non-conservative force, simply get rid of it, and then we can simply minimize this excess term too. So we can essentially minimize them independently, and we can simply get rid of this term, and the minimization of this excess term will essentially give us this weighted Wasserstein to geodesics. Now, because we know we don't have access to non-conservative forcing, then we really have to deal with a very non-trivial trade-off between excess entropy production that we have to incorporate if we're trying to move from one state to another. This is sort of associated to dissipation in the standard sense, and this housekeeping entropy production that we have to incorporate if we have circulation in our velocity, if we have those particles sort of swirling around the origin without any net motion, really. So in order to illustrate this and to sort of wrap up, let me show you this sort of numerical example in which we try to solve entropy minimizing cycles. So what we did is, again, we went back to our Brownian gyrator parameterized by R and theta. So again, all of the points in this plane are different distributions, different states of our thermodynamic system. And what we did is we started and ended a cycle at this point, and we tried to minimize entropy over a cycle. Now, if we do this in the standard case, in the isotropic case, where we only have one temperature, we're trying to go from one point to the same point while minimizing entropy reduction, the optimal thing to do is just to stay there, because minimum entropy production can really be characterized as the length of this path. So we don't perform any path, and then it's zero. But now, because we have this anisotropy and we don't have control over non-conservative forcing, we can no longer characterize our minimum entropy production by this distance. And we will see, what we saw is that the longer the time period of our cycle, the closer our system gets to this horizontal line. Now, this horizontal line, as I sort of said before, this corresponds to theta is equal to 0, which corresponds to our system being uncoupled and to us being at equilibrium states. So we really see this trade-off between the entropy that we have to pay for essentially moving and the entropy that we have to pay if we are not at equilibrium. So with this, let me now just wrap up sort of a very brief review of what we've done. Hopefully, I've conveyed sort of this idea that really this geometry that optimal mass transport brings to the table can be very useful in the stochastic thermodynamic setting, and especially if we're dealing with thermal isotropy. So we've seen how maximum work output is related to an isoperimetric problem, and maximizing efficiency is related to finding an isoperimetric inequality for our space of thermodynamic states. We've also seen very, very briefly that minimizing entropy production in this thermally anisotropic setting is related to this trade-off between Wasserstein to geodesics and housekeeping entropy. So with this, let me thank you for your attention, and also thank the team. Amir here, Yongshin here, Gerald here, unfortunately I don't approve it, and also the funding of my PhD.
Olga had already a bunch of questions in the seminar, but if you have some more.
Yeah, have you thought about how all this plays out in quantum systems?
So, I mean, I've tried to think about it. For what I know, some of these things can be generalized. The thermally anisotropic setting, I wouldn't even be able to begin to talk about in the quantum setting. I don't even know what it would mean. But I guess, I mean, some of this, I guess the stochastic thermodynamic framework, some of it can really be applied also to settings, but maybe you guys know better than I do.
And maybe you can walk us through this slide you had about the energy harvesting, the physical system.
Which one do you mean?
Yeah, just those cartoons you showed. So go forward.
Oh, forward.
Yeah, these. Yeah. So tell us more about this, what you have in mind here.
Yeah, so here, so in the first part of the talk, we were trying to extract energy by externally manipulating this potential. But the thing is that typically in microscopic systems, to be able to externally manipulate this potential, you have to put more energy into the system that work you can get out. And this is not what we want, right? So it's really interesting to be able to try to make these engines autonomous. And this is what we tried to do, and this is what we came up with. So this here this circuit essentially exemplifies the Brownian gyrator sort of electrical embodiment. So if we didn't have anything inside the capacitor plates and this wheel, if you forget about that, that's simply the Brownian gyrator. Now, what we showed is that we can couple this Brownian gyrator through some dielectric padding in this capacitor plates to an inertial wheel. And if we couple it in a smart way, then we can show that for big enough inertias, essentially, we can have an unstable periodic orbit that is work extracting. Essentially, this is saying that this engine works, that if we start with some velocity of the inertial wheel, then this wheel will keep rotating while we're extracting work from it. However, in order to be able to do this, we require inertia of the wheel, which again, I mean, sort of just because we are inspired by biological systems, this is typically not the case there, as we talked about. So what we did in another work is we showed that we can couple several such engines in a sort of symmetric way. And in this way, we can really get rid of this need for inertia. And we can really have stable periodic orbits for arbitrarily small inertias. And this is really reminiscent to this cartoon, which this is a rotary motor. This is the bacterial flagellum. And in this type of rotary motors, which again, we don't really completely understand, there are several torque generating subunits. And this one, in this case, is I think 11-fold symmetry. So we're essentially sort of motivated by this type of engines in which we can see symmetries. In the ATP synthase, for example, you also have the same thing in which I think you have 3-fold symmetries. So we're really inspired by this. Even if, again, our setting is like a lot simpler than the complexity of this type of engines.
Great. Any other questions?
I didn't actually understand why you need to minimize the entropy.
So, I mean, especially in the setting of thermal anisotropy, I don't know if I have here.
What was the question? I couldn't hear it.
So I didn't understand why you need to actually minimize the entropy. Like when usually systems tend to follow trajectories which maximizes entropy naturally. So
yeah, so I guess we are seeing here low entropy states as resources. So in our case, we have this type of systems in which we assume, of course, we have infinite heat paths, right? But this is typically not the case. And what would happen, for example, in this electrical circuit, is this electrical circuit, if we leave it by itself, it really has this non-equilibrium current going around it. So you could, I don't know, get some energy from that. The thing is that because these heat paths are going to be finite, there would be heat transference between the two heat paths, continuous, and this would essentially ultimately equilibrate these heat paths. And that would mean that we would no longer have current going around our circuit. So we really want to keep that fuel alive in a sense, right? So we want to preserve the low entropy states in a sense. So we want to sort of minimize this heat influx from one to the other while still being able to control our thermodynamic system.
So I would have also said that when you do these controls, you can do it in a wasteful way. You can do it in a way that spends your energy in a way you can't pull back the work extraction from. But then there are ways that if you do it in a clever way, you can extract more work, right? And so I assume what you're showing is that the work extraction is best when you minimize the entropy.
Totally. That's another way of looking at it through work. I mean, essentially, work is or dissipation or dissipative heat, what we're talking about, it's intimately related to entropy production, right? And in the same sense, if you want to maximize the work output, as Professor Jordan said, you want to minimize the dissipation, you want to minimize the work that you're losing through, this sort of entropy.
Lost energy. Okay, let's thank Olga again. If people want to join for lunch, I think we have to go to lunch a little early, but if you want to meet us in my office in a few